right? Don't worry about interrupting the class. Would like to address all of that before we go on to make sure that you keep up with what's going on. So in terms of the agenda for today, right? So I'll give you a bit of an introduction to why NFV exists today, right? We'll look at the second section is a primer, right? It's a primer for network engineers who are not necessarily familiar with virtualization technologies. It doesn't go into a lot of detail, but does cover some of the key elements of it, because it is absolutely crucial to how NFV is implemented in networks today. And then we look at the ETSI NFV ISG framework. I cover the 3 different elements of it: the NFV infrastructure, the management and orchestration, and the virtual network functions themselves. I'll talk a little bit. There's another section there that I seem to have missed out there. So right after that, we'll talk about use cases. So I'll take a couple of use cases just to give you a flavor for how it can be used, right? And then I'll look at performance, a very important perspective when you try and move, change from a purpose-built hardware architecture to one that is not. And a little bit about open source, what's happening in terms of the different solutions in the open source space. And I'll finally wrap it up with a summary of what the state of the industry is when it comes to NFV. So hopefully that gives you a sort of reasonably well-rounded picture of this whole space. It's a very complex space. I cannot imagine I can cover all of it in 3 hours. But what we do is give you a broad look at it so that you have the means to be able to delve deeper into it. Okay, so introduction, right? I like to sort of abstract some of these things that are happening in the industry from time to time. And when we look at what is happening with SDN, what's happening with NFV, then at a very high level, it's trying to strike a balance between specialization and generalization. Right? We know, no doubt, you've been in the industry for a while, and this is a cycle, right, that happens over time. Just like there are cycles of outsourcing, may not be able to do it in the most optimized fashion. So when we look at NFV, it's really this thing that drove NFV, right? Specialization versus generalization. And so I consider this as one of the inflection points in this continuing cycle. So you look at routers, right? They're actually another example of it. And we I don't think any of us were there back in 1969. I hope not. But we started off with the first router for the ARPANET, called the Interface Message Processor. Rugged-looking thing, right? You have a look at it; it looks pretty solid. Custom design for a routing function. As time went on, the applicability of the router grew to encompass more protocols, right? Because we had a variety of protocols, right? I remember when I first came into the industry, and I was studying for my CCNA exam. It was a bit of a nightmare because you had DECnet and AppleTalk and SNA and all these other things that I've forgotten now, IPX. So we had lots of these protocols. There was no real winner at this point, right? So routers had to support all of these protocols. As time went on, IP obviously became the most popular one because the web became important. And so routers started getting more specialized towards IP. So instead of having a general purpose router that could do everything, we now had the emergence of chips that were optimized for IP. So you see that cycle once again, right, of generalization versus specialization. Now, let's say the 5-6 years prior to NFV, what happened was that routing vendors decided to differentiate platforms not just based on routing capabilities, right? Routers do routing, right? And it's not, okay, I'm not going to say it's a simple exercise, but it's well understood, right? They run routing protocols, they do forwarding. But then we started seeing a lot of these application layer things coming into routers, right? We had DPI functions, we had firewall, we had caching and so on coming into routers, which weren't really designed for that function, right? So that is the point at which I'm going to stop, and this is where NFV kind of comes in, okay? So the important thing to keep in mind is that we, as an industry, we saw that there's a lot of functions that routers are performing. There are lots of specialized appliances as well, which were designed for this function, like firewalls, like intrusion detection systems, intrusion prevention systems, and so on. So many different appliances emerged as well that weren't they weren't actually routers as such, but they were performing an application function. Okay, so the routers over time grew more complicated, right? And when we once again abstract things out and look at how we've dealt with new applications and new challenges in the datacom industry, it kind of comes down to, when we have new problems, we like creating new protocols, right? So for those of you who are involved in the IETF and so on, it's cool, right? We have new problems, we come up with new protocols. We then come up with specialized hardware, right? So that these new protocols can run on this new hardware. And we've done this for a long time. And we've reached a point where things have gotten pretty complex, right? Today's networks are very complex. The devices are actually very complex. And complexity is not a good thing, right? I mean, you want to solve your problem in the simplest possible way, right? Not any simpler, of course, but the simplest possible way. And that is not always apparent to us. So, another example of that is, if you look at like a real example, this is an ATCA platform, right? So an ATCA is a standard sort of architecture that was designed in order to provide a standardized sort of hardware mechanism for building platforms. And you see a lot of sort of more control plane functions, such as some of the stuff that happens in mobile core networks, basically signaling functions and session setup and so on, happens on specialized devices like any ATCA platform. And when you look at an ATCA platform, it actually has many different types of blades in it, right? So some have dedicated processors for running different applications. Some are for controlling the system. There are some that are there just for I/O, right? So your basic routing function, input and output. And then there are application-specific cards as well. So we end up with all of these different things running on specialized hardware. So this is one example of where you've got a disparate variety of things running on the same piece of hardware, except the hardware is sort of more custom designed than a general purpose platform. Okay, so summing it up, right? The world before NFV. I've tried to sort of summarize it into a few things. So firstly, it's characterized by specialized network software that's running on purpose-built hardware. So the key thing to take away from here is that what we're trying to attack here with NFV is purpose-built hardware, right? So today, the vast majority of systems are like that, right? You can't separate a firewall software and run it on something else. Right? It goes hand in hand. It's tightly coupled. So you end up needing different types of hardware devices for different functions. As a result, right, all of these have to be dimensioned separately. The way you dimension a firewall is very different to the way you dimension a let's say, a carrier-grade NAT device or a router, and so on. They have different points at which they scale. And they have different hardware life cycles, right? So you have to swap out hardware quite often. So this is a very, I guess, complex exercise. And working with a lot of service providers myself in my current role, I know that even upgrading software takes a year, right? By the time they've tested it, they've rolled it out to the network. Forget about hardware. So it's a real challenge for operators out there. So in 2012 at the SDN and OpenFlow World Congress. So back then, SDN and OpenFlow were kind of synonymous, right? It's not the case anymore. But we had this conference in Germany, and there a bunch of 13 carriers, some of the largest carriers in the world. So you can look at the names there: AT&T, Verizon. We had NTT, KDDI, Telefonica, right? Some of the key proponents, they got together and they published this white paper. So if you haven't read this white paper, please do so. It's a very, it's a small white paper actually, but it outlines the problem pretty well. I will summarize it for you, of course, right? And what they said was we've got to solve this problem. So the things that I just mentioned here that are creating complexity in network environments need to be addressed somehow, right? And they had a high-level vision of how that could be done. So, NFE was really born in October 2012. It's not to say that operators were not independently applying similar concepts. They were, but as a unified sort of action, it really started in 2012. So it's like 5.5 years now, right? It's been a while. Now, the very next year at the same conference, they issued an update to it, and there they gave an update on what was happening from a specification perspective, right? So I'll talk about that. But essentially, what happened was that as a follow-up to the white paper, these operators got together and they established a new what they call an industry specification group, an ISG, within ETSI's standards development organizations framework, right? So ETSI is a what does it stand for? European Telecommunications Standards Institute, something like that. So they as you may know, they're pretty involved in driving standardization of telecoms equipment. So they created this new working group, or the industry specification group for NFV, right? So they gave an update on that, and there is a further update that came out the following year. So there are 3 white papers that it may be quite instructive to have a read of. Okay, so what did they actually articulate, right? So I've summarized it for you in case you don't have the time to read white papers. 4 things. So they identified that in their networks, right, and these are the top 13 operators in the world, or no, 13 of the top operators in the world, I should say. They identified that they've got a large number of very diverse devices in their network, right? It's nothing, it doesn't come as a surprise. They said it's getting very hard to actually find the power to drive them, find the skill set to be able to operate across so many different platforms. And it's just getting very complex for them to manage a network that has all these different elements, right? They also said that every time they want to create a new service, it requires new hardware. And so it's compounding the problem. And finally, they highlighted that the life cycle of hardware is getting shorter and shorter. For those of you who were here yesterday afternoon, you would have heard about what's happening in terms of processors and cooling and memory and so on, right? So the life cycle is actually getting faster. We know that, and that means in order to keep up with it, you have to upgrade. Bandwidth is doubling, tripling every year, right? So you have to the life cycle that you have is getting shorter and shorter all the time, which is creating a real problem. Right now, there's not much you can do, right? As customers move from, as your devices move from 1 gig to 10 gig to 100 gig, and now 400 gig, you have to keep pace with it. So it's a real challenge for operators. So, the outcome of that is it's quite slow to roll out new services because you've got to deal with all this complexity that has been created in networks. Okay, so here I want to define a term. You may have heard of it, you may be familiar with it, but just in case you're not, the term is disaggregation, right? So we've been hearing a lot about disaggregation over the last few years. And disaggregation basically is, it's to take something and split it up into its component parts, right? So we take a large thing, take a car, split it up into tires and bonnet and seats and steering wheel, that kind of stuff, right? So we take this entity that is complete by itself and split it up. So from a network context, it means we take an integrated system, call it a router, call it a firewall, right? And we split it up into a number of different components that actually make sense. Now, why would you do this, right? One of the reasons that you'd want to do this is if you've got a very large, complex system that is operating like a black box, then whenever you need to do anything to the system, upgrade it, scale it, and so on, you've got to replace it with another system that is larger, that is another black box, right? If you have the ability to split this up into its individual components, then each of them can scale independently, right? So imagine, like keeping up this car analogy, which is not really a very good analogy, but let's just say you bought a car from BMW, and they said the only tires that can be used are BMW tires, right? We'd have a bit of a problem, wouldn't we? That would not work too well. Or the fact that every time you had a punctured tire, you had to buy a new car. Not a good situation. So the idea is that you've got to be, if you split it up into its individual components, then you can buy best of breed for all of them. So you buy your tires from Michelin or whatever, and a battery from whoever makes batteries, Samsung, or maybe not. Yeah. So there's few. I mean, it gives you that flexibility that we do not have today, right? Okay. So the basic model for NFV that was propounded was, and you probably can't see this too well, so I'll read it out. This is a figure straight from the first white paper, right? So you see that the operators identified a number of different devices. So routers, CDNs, SBCs, WAN acceleration, firewall, packet core elements like SGSN, GGSN, provider edges, BRASs, even things like radio access nodes, right, for those operating mobile networks. And they said, what we want to do is keep the software. Take the software out of these, right, because that's the real brains of it. And be able to normalize the hardware to industry standard service. So basically service, right? Can we do this? Can we take the actual function and run it on standard service? So that instead of having all these different devices here, for hardware purposes, we've just got service. And we run different applications on servers just like you do today, right? So that was the challenge that they set the industry. And this is what they wanted. So I apologize for the colors. They're not coming up too well here. So this is an example of a vertically integrated system, right? A purpose-built platform. You've got some sort of software running on some sort of hardware. And you cannot split the two, right? They're tightly integrated. You cannot take the software out of one and run it on another. You can't take Cisco iOS and run it on a Juniper router, for example, right? So it's tightly integrated. So what they wanted to do was split the two, right? So you probably can't see the difference between the two, but there's a white line here because it's just separating the two. So we take so instead of purpose-built hardware, we run it on COTS hardware. So COTS stands for commodity off-the-shelf, right? Hardware. So just another term for industry standard hardware. And industry standard is not so much a standard, but a de facto standard, right? The fact that we tend to use Intel servers out there. Intel is still the predominant supplier of servers or CPU technology out there. And we take this function that was previously running on an appliance and we virtualize it. So virtual function simply means something that runs on commodity hardware, right? It's not anything different. It's just that it's running on commodity hardware. There's still software, right? Even this is software, except that you cannot extract it out of the system. Okay. So before I go into this, is everyone clear about the difference between NFV and SDN? Does that mean yes? Can anyone volunteer here? Yeah. Do we clearly understand the difference between NFV and SDN? I'll give you a mic, because we've got a recording happening here.
Yeah, NFV is basically, virtualizing various functions. As you explained, you kind of, moving away from a black box and then taking the function and, deploying it into a, off the shelf, typically a, server specific. It could be an Intel or, AMD or any of those chipsets, which basically, it's a standards, the hardware is basically available, off the shelf, and it's not a custom specific hardware. Whereas SDN, defines the automated way to kind of, build those functions, or the way those functions should actually, drive the traffic. It's like kind of, in a virtualized environment, because you would have multiple functions which should be residing in a single device. So SDN will kind of help you in terms of, driving the traffic flow or service chaining.
Very good. Yeah. So that's pretty much it. The one thing I would add to that is that while NFV separates the software from the hardware, SDN is talking about separating the control plane from the data plane, right? So it's not, SDN is not so much about software versus hardware. It's still within software, but it's trying to optimize where control plane functions actually reside in your network. So very quickly then, NFV, you've already talked about physical appliances. We virtualize the application and run it on industry standard servers. It's not just servers, right? It's predominantly, we talk about servers, but we're talking about virtualizing switches, storage, network, everything. And SDN, we take these monolithic, right, switches and routers, which monolithic as in they're integrated unit. And what we do is we extract some of the control plane functions out of it into a centralized controller so that they can now control all of these devices. So we're still doing a split of some elements of software, but it's not so much a software split as a functionality split, right, between the controller and the actual devices, the forwarding elements in your network. Okay, so I hope that's clear. So, okay, showing this another way, same sort of analogy as NFV. So you see, today's vertically integrated system, right? So today you buy a router, for example. You've got forwarding hardware, your line cards. You've got a network operating system. It could be, like I said, iOS or Junos, or in the case of Nokia, the SR operating system. And then you run, you don't actually run, but the operating system has built-in applications on it that help you to run your network. With SDN, what we're doing is we're separating all these. We're saying, make these forwarding elements simpler, so that they still have the forwarding hardware, but the OS is a bit lighter weight than the OS that we currently have. So it doesn't have all the functions. It still has a fair few functions, but we centralize some of these functions to what we call the SDN controller. And then we expose interfaces from this controller that can be used by network applications in order to create innovative applications, right? Something you can't do today, right? You can't write code and get it to run on a router. That would not work too well, or at all. So that's SDN, right? So the predominant reasons articulated by these operators as part of the push was, okay, so we're separating the hardware from software, and we're using COTS hardware. Now, what we're getting out of this is, firstly, the economics part of it was very important for operators at the time. And they said, by doing this, we can vastly reduce the cost of hardware. So that was one. The second one was to make it more open, as I described. So you can have best of breed. You can buy best of breed hardware. You can buy best of breed software. Everything works together, and it's all cool. Time to market. There was an expectation that if you can decouple all of this, then instead of focusing on hardware, operators can focus on software, right? The functions themselves, which are much easier to do in a lab environment, for example, right, than it is when using purpose-built hardware. So they'll be able to get services to market quicker. Operational efficiency, I'll talk a little bit about that as well. It's like, how do you scale functions, right? We spoke about that. What happens? Let me give you an example, right? Say you have some CDN, on-net CDN caches in your network. In today's architecture, you have to dimension them for busy hour, right? So if you're expecting 100 gigs of traffic during busy hour, your caches have to be dimensioned for 100 gigs. Now, during off-peak times, it may well be only 10 gigs. So you've got 90 gigs of capacities that is sitting there idle for large parts of the day, and you cannot do anything about it, right? So the hope was that with virtualized infrastructure, you would only build capacity as needed, right? So when you need that extra 90 gigs, you instantiate more servers. And when you don't, you take them away, you tear them down. And the final was multi-tenancy, right? We get better use of resources. So instead of having just a single function running on a hardware platform, you get multiple functions running on the hardware platform at the same time. You get better utilization. So that was the hope of it. Now the enablers, well, let me just go back. For this to happen, we've got to have some underlying technology that can help us, right? And the first, most important thing that operators were hoping to exploit was cloud computing, right? So with cloud computing, we've got hardware virtualization, which allows us to run multiple virtual machines on a single platform. For the multi-tenancy aspect, that is very important. We had Ethernet virtual switches, right? So switches, switching in software, lots of innovation in hardware, right? So multi-core CPUs. So today you can buy some pretty grunty CPUs. Like we saw the ARM64 yesterday, right? For those of you who were here, even with Intel Xeon, you can get 22 cores, even more, right? So you can get there's a lot of hardware capacity for processing. Smart NICs, where you can offload some of the CPU functions that were normally or previously done by CPUs onto hardware, like the NICs themselves. So there's a whole ecosystem around this that's used to build cloud computing infrastructure that we felt we could actually exploit here. And the second one was COTS hardware, right? So if it's a very competitive market for COTS hardware. They're used everywhere. They're cheap, right? In the scheme of things, when you look at COTS hardware versus proprietary hardware, then they're gonna be cheaper, at least from a capex perspective. So there was this intent to take the best of these and apply this to NFV. Now, what are the challenges, right? So I'm sure most of you, like you said, you haven't actually implemented NFV in your network today. So you're using standard sort of hardware, routing functions, appliances, firewalls, and net devices, and WAN accelerators, and IPsec gateways, and all that kind of stuff. So clearly, you're using that today, right? To migrate to an environment where you split the function from the hardware, there's a few challenges, right? So the challenges that were initially identified was that for this to really work, then we need true portability. So if I've virtualized some software, let's just say I've got a virtual firewall, right? It's only useful if I can run it on different types of hardware. If it only functions on certain types of hardware, then the portability isn't there for us to be able to exploit all the benefits of NFV. It's got to interwork in a mixed environment, a hybrid environment. Not everything will move to NFV, right? And this is not just now. It may never happen. There'll always be a need for specialized devices. So you'll have this hybrid environment. How do you interwork with this? How do you evolve the operational support systems, your business support systems, to exploit the benefits of virtualization? I'll touch on this later. It's a very complex exercise, right? And we kind of stuck there right now with a lot of operators. How do we manage these devices? How do we orchestrate these devices? How do you get the right level of performance? Right, today you buy routing platforms and so on. How do you characterize them? Like you say, okay, I bought a 100 gig blade, and that blade gives you 100 gig, right? When you buy servers, you don't say I'm buying a 100 gig server, right? You spec a server based on different things like number of CPU cores, amount of memory, the types of NICs, and so on. So it's a case of trying to achieve a similar outcome with COTS hardware that we have with purpose-built hardware. And we can support multi-vendor environments, right? By definition, because if you have to split this up, you don't want to end up in a situation where you buy software from vendor A means you buy hardware from vendor B, although they are open now. There should not be that restriction. So it's got to be very, very portable across all of these applications. So that was one of the challenges, right, that we have to surmount. So what happened was that, as I mentioned, the operators got together and founded this industry specification group within ETSI called the NFESG. And it's very interesting that when Etsy ISG was founded, the mandate was not to produce standards, right? Although the Etsy is a standards development organization, what they said was that initially what we're going to do is we'll come up with the concepts, the framework, the architecture, and we'll work with other SDOs, like ITUT and IETF and so on, and drive standardization through these SDOs, which had obviously implications for it, right? So at the end of the first phase of the ISG, they produce a number of documents. Even if you do nothing but else, I think it's worthwhile reading some of these documents. So there's only 5 documents there, as I've listed there: use cases, there's some requirements, some terminology, and architecture. They're not very long documents, but it gives you a good flavor for what NFV is. I've summarized that as well through the course of this presentation. Okay, in the second phase, right? So the first phase was 2 years, and the ISG then extended the life for another 2 years because the work wasn't quite done. It may actually never be done, right? And here, what they set out to do was change a little bit of what they were talking about, right? So instead of it was quite apparent that having an architecture without standard interfaces was not going to work, right? How do you build interoperable solutions if there is no standard to adhere to? So in release 2, they started focusing on some of these interfaces, right? And I'll take you through these interfaces. They probably won't make much sense right now, but they've come up with a set of 11 documents that not further, but they actually detail some of these interfaces and the information models that are tied to these interfaces, right? So I've already spoken about release 2. Now, it's in its 3rd phase now. So at the end of the second iteration of documents and so on, the ISG recharted for another couple of years, and they're working on finishing some more of this interface specifications, and really working on the implementation side of NFV now. So it's, as you can see, this is 5 years now. It's a lot of work. It's not easy to change direction in terms of how we build networks. It doesn't happen overnight, right? So there's still a lot of work to be done, but we're making good progress. That's the probably key takeaway. Okay, so that was a brief introduction, and I've kind of referred to what's coming later as well. Do we have any questions while I grab some coffee? All right, so looks like it makes sense so far. Great. So what we'll do over the course of the next half an hour or so is give you guys a bit of an introduction to virtualization. And this is purely a compute capability, but it's actually quite important to how we build virtual networks. Okay, so server virtualization, this was something that was pretty much pioneered by VMware, right? When they came with virtualization technology, is there for a very good reason, right? So there was a recognition that when we have applications running on servers, then we find that we're not actually utilizing the full capability of servers, right? So you have cases where the CPU is only running 2-3%. You're only using a bit of the memory. And so when we build server farms where we have a single application, for example, tied to a single hardware server, then you end up with a lot of wastage there, right? Because they're not actually utilizing the full capability of the server itself. So what was required was to somehow pool these resources so that we can get better efficiency. If you got servers that are running at a very low utilization, then why don't we actually use that spare capacity somehow, right? And as a result, we reduce the power requirements, the space requirements as well. So while doing that, there's still a requirement, right, that even if you will consolidate multiple servers into a smaller number of servers, we still need to provide isolation between applications, right? That's part of the reason that you would run different applications on different servers, is to provide that level of application isolation between these servers. So that was important, that we did not actually want to compromise that. At the same time, when you have different applications running on the same server, you do want to allocate them certain minimum resources, right? So if you've got 16 cores, you might want to say, if I'm running 2 applications, they each use 8 cores each, if they're capable of, right? So that way, you have that deterministic sort of behavior of these applications. And secondly, and thirdly, I should say, is when you do that, you do not want to lose performance, right? It's no good gaining that extra capacity if you lose performance. So performance is obviously very important. So a number of technologies emerged, right, which I'll take you through very quickly. So one is emulation, right? So when we say emulation, what do you mean? It means to make one system behave like another system. And let's look at this from a hardware perspective, right? So for example, like when I grew up, I used to play the Atari 2600 games, and I wanted to show my kids what it's like, so I downloaded an emulator for my Windows PC. And obviously, what that does is, as you know, it recreates that Atari 2600 architecture that you can run those ROMs on it. So that's an example of emulation, right? So, and this one here plays Sega Mega Drive on your PC. It generally has a huge performance impact because you're getting your underlying hardware to do something it's not really designed for, right? And so normally this emulation happens in software, and it slows everything down majorly. But it's useful, right? Because if you cannot, hardware gets obsolete and so on. So if you cannot procure new hardware, what do? If you have to run these older applications. So emulation has a purpose in the network, right? So that's emulation. So in this case, as you can see here in the diagram, so we've got some sort of system. Let's just call it a virtual machine. And this system, let's call it software, right, is not modified. So the software does not know that it's running in an emulated environment. So it thinks it's got access to all the hardware that it's designed for. So it makes these calls to hardware through its hardware drivers, device drivers, that is not changed. So the emulating system, right, what it does is it actually traps these calls and converts it, or actually, no, it actually handles those calls. So that to this system, it appears as if it is running on its native hardware. So that's the whole concept of emulation. Now, like I said, it's a bit slow, so not the best idea. So this is where full virtualization comes in. This is what was invented pretty much by VMware. And what full virtualization means is that what we're trying to do here is provide pretty much an emulated kind of environment for different applications, so that the applications do not have to be modified, right? So it is just like emulation, except when we talk about full virtualization today, what we do is we actually exploit the capabilities of hardware. So for example, with Intel, you've got the VTX capabilities that lets you do hardware virtualization, right? And that can be exploited by the hypervisor in order to provide virtualization. So what's a hypervisor? It's a piece of software, right, that sits between the users of the system and the underlying hardware. And it presents to the applications a virtual hardware environment that looks just like the actual hardware that the virtual machine is expecting. So this is like emulation, but this is emulation with the use of hardware mechanisms in order to support it. All right? So when you do this, you get an outcome that is a lot more efficient. In terms of performance, it'll be a lot better than software-based emulation. So as you can see here, right, from the perspective of the virtual machine. Now, virtual machine is basically that an emulated environment that is used in order to give the hosted virtual machines a perception that is operating with real hardware, right? So these virtual machines are using the normal drivers to talk to hardware. And it looks like there's no change. Now, the VMM here that stands for Virtual Machine Monitor, right? Also called a hypervisor. I'll be calling it a hypervisor from now on. It's just a little bit simpler. So like I said, it's a piece of software that interfaces directly with the hardware, but presents an environment to all of these guys that looks like real hardware, right? You get me? So this way, you can run many different machines on a single physical machine. And that's why we call it a virtual machine. Because all of them think they have the entire thing to themselves. So once again, a bit of terminology. The virtual machine monitor, the hypervisor, it may be running over an operating system. It may or may not. We'll look at it a little bit later. But this operating system is called the host operating system, right? It's the base operating system of the system. And then the virtual machines, they all have their own operating system as well that they're running within the machine. And that's the guest operating system, right? Now, typically, the guest and host have to have the same architecture, in this case, x86. Okay, so that's full virtualization. Now, there is a bit of a twist to it as well. So you can do what is called para-virtualization. And this is a kind of virtualization where the guest operating system is aware that it's operating in a virtual environment. So instead of making direct calls to hardware, what it does is that it actually makes calls to an API that is exposed by the hypervisor. Now, why would you do that? Well, you do that to get better performance. So in the absence of, for example, hardware mechanisms for virtualization, this provides you a much more efficient implementation, and your performance will be a lot better than if you actually than if you did not use it. So the guest is aware that it's running in a virtualized system, and today most OSs have that built in to them, right? So there was a time when you had to patch operating systems in order to get that capability. Today most of them ship with it, so it's nothing new here. So here's what it looks like. So the virtual machine uses modified drivers, whereas in the full virtualization case, as you saw, it was using the native drivers, right? The real drivers to drive it. And the hypervisor is expecting these, and so it communicates using that. The hypervisor itself talks to the hardware through a real driver, right? Okay. Now, it's not either or. You can have both, right? So you can have systems that do both full virtualization and para-virtualization. So, for example, KVM is a full virtualization solution, right? It requires hardware assist for virtualization. So in order to virtualize, for example, the processor, the CPU, it uses full virtualization. But at the same time, you can use a library, the VirtIO library with KVM that allows the VirtIO drivers on guest machines in order to communicate with KVM. And that way, you get much better I/O performance than you would get otherwise, right? So that is an example of a system that is actually using the best of both worlds. So using both hardware virtualization for CPU and para-virtualization for things like storage and I/O. Okay, so touching on this again, so as I said, the hypervisor, also known as a virtual machine monitor, it allows the capability to host virtual machines, right, on a single physical machine. And its job is to arbitrate between the two, right, to provide resources to the virtual machines that the virtual machines actually need in order to operate. Okay, I'll keep going. So in terms of hypervisors, there are two types of hypervisors that we need to be aware of. Firstly, there are type 1 hypervisors. And type 1 hypervisors are those that actually run directly on the hardware. So you see that in this case here, we've got a native hypervisor, a type 1 hypervisor that is running straight on hardware. And what I mean by that is that it does not actually need an operating system, right? It runs directly on hardware. And it gives you better performance because now you do not have to interface through an operating system. The hypervisor can communicate directly with the hardware. And on top of that, it exposes this virtual hardware that is now used by different virtual machines in order to operate on this single machine. So that's a type 1. Type 2 is one where you see this layer now, right? And you probably can't read this too well, but this is a host operating system. So the hypervisor runs on a host. So people who've played with things like VirtualBox, right? So VirtualBox just is an application that's running on your PC or Mac or Linux platform. And so that's an example of a type 2 hypervisor. It's actually using the capabilities of the operating system. So, like I said, there's a bit more overhead when using that platform. So you normally would not use that for production kind of applications, right? For testing purposes, for lab environments, that kind of makes sense. KVM. So KVM is a very popular open source hypervisor, you could call it. And KVM ships with Unix now. So what KVM does is it basically converts the Linux kernel into a hypervisor, right? So it's got a kernel module, and for the last 10, 12 years, it's been shipping as part of the Linux distribution. So it just comes with it. So there's a bit of confusion on whether it's type 1 or type 2, but it's really type 1 because now Linux actually becomes a hypervisor, right, with KVM. So it's not like Linux is running on top of another operating system. So it's kind of got characteristics of both here. Okay, some of the common hypervisors, as we said, KVM, quite popular. VMware, obviously quite popular. So these ones are probably the two most widely deployed ones. You've got Citrix Zen, which is based on Virtualization. Microsoft's got its own. You've got VirtualBox, as I said. You've got Parallels as well. So there's a number of different hypervisors in the market today. With a lot of NFV environments, it's mainly VMware and KVM for now. That may change, but that's the predominant deployment. So that's one technology for virtualization. The other one that is a bit of a competing technology to hypervisors today is containers, right? So anyone here across containers? Okay, there you go. So containers provide a viable alternative to virtual machines, right? They've got some different characteristics, and I guess the big one is that while virtual machines talk about machine virtualization in the sense that they try and present to these guests a complete machine, a hardware machine in a virtual fashion. What containers do is kind of do operating system virtualization. So they provide you with this context that is part of the that is done through the same kernel. So all of these containers are so a container would be equivalent to a virtual machine, right? From the context of separation, but they share a single kernel. And the kernel ensures that there is isolation between them. It uses the Linux concepts of namespaces and C groups and so on to isolate different processes with their resources. So to the containers, it kind of looks like they're operating in their own self-contained environment. They do share the same kernel, as I said. So that is a viable alternative. A lot of operators and the research community as well is looking into containers right now. Now, they do have a number of advantages over virtual machines.
Can we say type 2 hypervisors and containers?
Sorry.
Type 2 hypervisors and the containers.
Not really, because I mean the type 2 still exposes a complete virtual machine, right? To yeah, no, they're not quite the same because so if you look at let me just go back here, right? So if you look at how containers are implemented, so you'll have you've got the host operating system kernel. There's a container engine of some sort that's providing you that, like it could be Docker or LXC or whatever. It's providing you the context for the different containers. Now, each of these containers is comprised of the application itself, plus the binaries and libraries that it uses. Nothing else, right?
There is no guest OS here.
There is no guest OS. So that's a fundamental difference. And it makes a lot of sense, right, when you think about it. It's like, why do I need, if I'm running 16 virtual machines, why do I need 16 instances of Linux or CentOS or whatever distribution that you're using? It doesn't make sense, right? It's a waste.
But how does it from a system perspective, see, even without, containers, earlier also we used to have a web server or a, DHCP or a DNS running on the same server, right? So how does it kind of, differentiate running a web server and a DNS on two different containers than, running it as, a consolidated instance?
It's from an isolation perspective. So, when you're running multiple applications on a single bare metal server, you can't say, I'm going to give you certain memory, certain memory, this much CPU, that much CPU.
So the resource allocation can become better.
Yeah. So, and that is key to it, right? And that's both virtualization, containers kind of do similar sort of things about isolation, but it's all about isolation of resources, guaranteeing of resources. Yeah. So very interesting sort of developments here. Okay, so in terms of advantages, so no, you're not duplicating operating system resources, right? That's a big thing. So virtual machines have higher overheads as a result of that, and each of them is a complete machine. So it is very heavy, right? So virtual machine technology it's good, but it's quite heavy. So containers give you a very small, lightweight mechanism to achieve similar kind of things. You can get more. So for the same bit of hardware, you can instantiate more containers than you can virtual machines, right? So because it's smaller, more lightweight. So you're getting better scale out of containers. They load faster, right? They load a hell of a lot faster than virtual machines. Because you're not booting up a guest operating system and all that kind of stuff, right? So there's a huge difference in terms of that. There are some challenges though, right, in an NFV space. So the industry still needs to work out all the security implications of sharing the same kernel, right? It's been work done there. I'm not saying it's done yet or nothing's been done, but that there are still some implications when you share a single kernel as to what it can do. Second one, maybe not a big one, right? You are sharing the same operating system, right? So whereas with a virtual machine, you can run a Windows virtual machine, a Linux one, a Mac one, whatever you want, right? You can have different virtual machines sitting on the same physical hardware. Whereas with containers, you're kind of sharing the same one. It may not be a big issue for a lot of customers, right? Now, so in terms of outlook, we still see that container technology for NFV purposes is some ways away, right? It's not mature. And talking to some of the big operators, they still see that it's still about 3 or 4 years away before they will go out with production implementations of containers. And my sort of personal view here is that it's not one or the other, right? I think that there'll be use cases where you'll have both of them, right? You may use containers for certain applications and virtual machines for others in NFV infrastructure. Okay, so lots of different ones out there. Probably Docker is probably the most popular one out there, but you've got all these others as well. I'm not going to go into that in a lot of detail, but if you want to have a bit of a play, that's what you're looking at. So we do have options to pick from when it comes to containers as well. Okay, now we're going for time. So we've looked at this virtualization technology, right, which is part of cloud computing infrastructure, and this is the sort of technology that's been used to build public clouds and so on. But NFV is a bit different, right? So the thing is, I pointed out earlier that what we wanted to do with NFV is to exploit some of these enablers. Cloud computing was an enabler. COTS hardware was an enabler. But can we use it as it is in an NFV environment? The answer is no, right? We've got 5 years of experience now to say that we cannot use it without modification, without enhancement. And there's a few reasons why. So, all of this technology is great for IT kind of applications, but what we're building here is, a carrier application, right? So you're moving things that are part of your carrier-grade network onto compute infrastructure. And so you have some expectations out of it, right? So first of all, you've got to be able to build 5 nines architectures, right? How do you build 5 nines? Like, you know, if you start buying servers that are completely redundant and so on, you'll be looking at a lot, right? So you're probably looking at a 3.9 server in order to somehow build a bunch of 3.9 servers that give you the end-to-end 5 nines availability. So that means that you've got to architect your network differently. We need more real-time performance, right? If you get a unmodified sort of server today, you find that it's doing a lot of things well, but I/O is a bit of a challenge. I/O becomes a bottleneck, right? So if you look at servers, they haven't typically been optimized for I/O, whereas everything we do in our industry is about I/O, right? Getting throughput, getting the best possible throughput out of it. So that means we need to look at how we beef that up. The architecture now becomes a lot more distributed, right? In the sense that, you know, today when you have a traffic flow in your network from let's say the internet, the global internet to a user, your end user, it doesn't go through a data center, right? Does anyone have any kind of traffic flows that go through a data center? User traffic, not control plane. We don't have that. So now you've suddenly got a data center in the path. Except you don't normally have a data center in the path, right? How do you get a data center into the path? So we have to think about how do we get traffic into and out of a data center and to the points that we actually want it to go to. So we've got to do that. We've got to optimize the operation of this, right? So as an example, you look at routers that we get today. You can get routers that are multi-terabits per second, right? Nothing surprising. You get 16 terabit routers. How much traffic do you think you'll get out of a server? I mean, there's been, I don't know, there's been many sort of tests done, and depending on the hardware and so on, you could get a few hundred gigs out of a server, right? You'll be paying a lot more for it. But let's just say you get a server that does 100 gigs, right? Because you have to maintain the price performance. Now, 16 tera, 100 gigs, how many times that goes into? That's 160 sort of servers, right? For example. So it's what we're looking about is if you are to emulate the same capacity within a server environment, then you'll be looking at a lot more servers. So manageability now becomes important. Automation becomes important. It's not to say it cannot be done, but we have to think about how it's actually done. Security, right? This is once again now a carrier class equipment. Till now, we haven't exposed our COTS hardware, our servers, to the global internet, right? I mean, I'm sure you're using DNS servers and radius servers and all that kind of stuff. But the communication there is between those servers and trusted elements in your network, right? But when your data plane is going through it, anything could happen, right? They could craft malicious packets or whatever, and we have to think about it from a security perspective. So that becomes a challenge for us as well. So this is not straightforward. That's the point I'm trying to make here, right? Okay, so that's that's a bit of an intro to virtualization technologies, which will help us to understand the rest of the architecture, right, as it applies to NFV. Any questions? Anyone disagree with what I said? You can leave here. I'm kidding. Okay, so we'll carry on, and like I said, guys, just put your hand up if you have any questions. So what we'll be talking about for the rest of the presentation is really driven by the ETSI NFV architecture, right? This is the industry standard architecture that was defined by ETSI. And one of the points I was making is that the ETSI specifications were largely driven by operators, right? So this NFV was not a vendor-led initiative for obvious reasons, because vendors would like to keep selling boxes and do that happily, right? So it was an operator-led initiative. Vendors came on board, so they've contributed to it as well. But a lot of the specification work was, still came out of different proponents from the operator community. Okay, so the basic model of NFV that I sort of covered a little bit earlier was we take this vertically integrated system that is shown as having hardware, and it's got some sort of network function. Now, what we mean by network function here is some sort of network application. That function could be, I've given examples like firewall or a BNG or a provider edge or just a simple routing function, right? So that's the function that we're talking about. So we take that and with NFV we split it. The network function gets virtualized and the hardware becomes COTS hardware. Now the Etsy actually then took that model and said, that by itself is not sufficient, obviously, Just because you got a piece of hardware, a piece of software you can run on hardware, that will not actually solve anything for us, right? We've got to have a whole framework around it. And so they came up with a high-level framework, which I'll go into in a lot more detail. So if you're delving into NFV, you have to understand this reference architecture, right? Because it's key to understanding how all the bits go together. Okay, so let me start from, whoops, keep dropping it, from the right slide, which should be this one here. All right, so we start off with the NFV infrastructure layer, right? So this is the layer that provides the resources that we need in order to operate the virtual network functions, okay? So right at the bottom of it, you've got the actual hardware. So you've got servers, you've got storage hardware, and you've got network hardware, your actual switches and so on. You have a virtualization layer that sits on top of it. And that's normally, like we discussed in the last section, this is looking at hypervisors and that kind of technology. It could be containers, doesn't matter. But it's some sort of technology that virtualizes the hardware. And it presents these virtual compute instances, virtual storage instances, virtual network instances to the virtual network functions. Okay? So these virtual functions then run over the virtual instances of these hardware devices. Now, running across all of this is what we call the MANO function. And MANO stands for management and orchestration, right? And this is a very important part of this whole framework. So I'll expand that a little bit further. I think I've already talked about this, so okay, we'll go to the next slide. So this is a more detailed look at this infrastructure. Okay, so let me build this out, right? You can see that this framework is just a more detailed version of what I presented previously. The thing that I want you to keep in mind is that there are three components. The NFVI, which is the NFV infrastructure. We've got the VNFs, and we've got the MANO function, right? So three things. If you keep that in mind, it'll make it very easy to understand this. So within this, firstly, we've got the NFV infrastructure. I've already spoken about this, right? This is all the hardware that we need. So all the hardware bits that make a part of an NFV infrastructure, servers, switches, whatever network devices you have, whatever storage devices you have, fall under NFV infrastructure, right? The next bit is what we call the Virtualized Infrastructure Manager. So this, you will see, is part of this box that I've got enclosed with a dashed line sort of here. So this NFV MANO box has all the management functions. So when you look at the Virtualized Infrastructure Manager, what it's doing is it's actually managing these hardware resources, right? And so to put some context around this, this is something like OpenStack, which can be used in order to manipulate this hardware, create virtual machines, and manage the whole life cycle of virtual machines. So these are the two key things that are part of the underlying infrastructure of NFV. Now the next bit there is what we call a Vnf Manager. Now this is once again a new thing that's come about as a result of NFV. We never had this before. So the job of the Vnf Manager is to basically manage VNFs, as its name suggests, right? So its job is to handle the different aspects of a virtual network function, from its creation to its destruction, the entire life cycle of a virtual network function. And I'll go through in a bit more detail as to what these different functions are, because it's actually critical. It's that there is no analogy that we have today in a proprietary sort of environment where we have to do this, right? You have an element manager today, sure, but it doesn't really do that virtual network function management function that we have. And it's actually key to some of the benefits of NFV. Now, you see this interface here, right? So the Virtualized Infrastructure Manager talks to the NFV infrastructure, right? So it's got one interface there. Now the Vnf Manager actually talks to either an element manager, or it can talk to the VNF itself, or it can talk to both of them, right? We've got interfaces there. There are lots of interfaces in this that we need to get familiar with if you get into NFV. It also communicates with the top level there, which is the NFV orchestrator. So what does that do? Now, what is a VNF? A VNF is a virtual instance of a single network function. So it could be, I keep using the firewall example. It's just as good as any, right? It could just be a firewall, for example, right? So one function. Now, when you're building a service, an end-to-end service, so for example, it could be a secure internet service or a mobile service, for example, then you have to build a chain, right, across that links the user to the actual service. And as I indicated, right, today the way we influence what a service is through routing, right? So if you want a bit of traffic to go through a firewall, you put a firewall in front of a router. There's no magic to it; it's physical. So that there is no other way to enter the router except this firewall, right? So it's a very physical thing. Now imagine you've got these servers sitting in a data center. How do you get traffic to it? No, you can't just connect up servers to each other, right? That doesn't work. You've got this infrastructure in place there. So what the NFVO does is it creates this thing called a network service. And I'll go into a bit more detail. But a network service is basically a collection of network functions that together form a complete end-to-end service. So this is how you link up the different virtual network functions. And so things like service chaining become important, right? So that you're able to go from one application to another. So that's the job of the NFV orchestrator, and it maintains the complete life cycle of the network service. I've got examples to make it all clear. So the NFV orchestrator communicates with the Vnf Manager, because in order to build the end-to-end service, it's got to talk to the Vnf managers. It has to allocate resources as well. So it talks to the Virtualized Infrastructure Manager as well. And it may talk to the OSS BSS systems too. So you can see it's a bit of it's a somewhat complex architecture. So by the end of this section, hopefully I've demystified some of this for you. There are many reference points. Now you can see that there are execution reference points, and then there are main reference points, and there are other reference points, right? So there's only one execution reference point. This is between the VNF and the infrastructure, because that's where the VNF executes, right, within a virtual instance of some sort of hardware. And then the other ones that are solid lines are the interfaces that are being defined by the etc NFV ISG. The dotted ones are there, but they will not be standardized, right? I mean, they could be de facto standards. It could be defined by other SDOs and so on. So a lot of these are being defined. You see that all of them have a name, right? So for example, this one has OR-VNFM because it's going from the orchestrator to the VNFM. Now the way to work out what these interfaces are is, so if there is an interface from the orchestrator to the VNFM, you find that the name of the orchestrator goes first. So it's like top to bottom. So VNFM to the Virtualized Infrastructure Manager is VI VNFM, right? And so on. So there's a whole bunch of these interfaces that we have to sort of consider here. Okay, so in the next part, I'll be taking each of these in turn, right? So that it really, you get a feel for what is involved as part of each of these different elements of the infrastructure. So the NFVI, so anyone, NFVI, what is NFVI? We're still awake? Anyone, what is NFVI? Sorry, who's that?
Yeah, the hardware infrastructure where you implement the network function virtualization.
Okay, cool. So some of you are awake, so that's great. So that's where all the hardware resides, and it presents a virtual instance of it to the VNFs that are running on it. Oh, it's almost break time. Okay, we might. I'm being given the indication to break here. So we might break for half an hour. We'll come back at 11:30. We'll finish off the framework and start looking at some of the more real applications of it, implications, and what's happening in the industry. If you have any questions during the break, feel free to ask. Thank you.